Hello, in this video, we are looking at another example of finding a Taylor polynomial of a particular order, and then using the estimation of the remainder to see what we can find out about how accurate that function or that polynomial is to the function. So we have the question, find the Taylor polynomial of order n equals 4 for the function f of x equals cosine x centered at a equals 0. Remember, the fourth Taylor polynomial is going to be the value at a over 0 factorial x minus a to the 0 plus f prime of a over 1 factorial x minus a to the first plus the second derivative at a over 2 factorial x minus a to the third squared plus the third derivative at a over 3 factorial x minus a cubed plus the fourth derivative at a over 4 factorial x minus a to the fourth. So we are trying to fill in these a's and the functions. The a's are all zeros, but the function part, we have for our n's, we'll have from 0, 1, 2, 3, 4. Our function is is cosine x. The derivative of cosine x is negative sine x. The derivative of negative sine x is negative cosine x. Derivative of negative cosine is sine, and derivative of sine is cosine. And these values, when we plug in 0, the center, we have cosine of 0 is 1, sine of 0 is 0. So we get 1, 0, negative 1, 0, 1. So we're going to plug that into our formula. So f of a is 1 over 0 factorial is 0 factorial is 1. X minus a to the 0 we define to be 1. So plus 0 over 1 factorial, x minus 0 to the first, plus negative 1 over 2 factorial, x minus 0 squared, plus 0 over 3 factorial, x minus 0 cubed, plus 1 over 4 factorial, x minus 0 to the fourth. And simplifying this down, all these zeros we don't need to worry about. And the 0 over 3 factorial is 0, and 0 over 1 factorial is all 0. So this is 1 minus 1 over 2 factorial times x squared plus 1 over 4 factorial x to the fourth. So there is our approximation. 1 minus 1 over 2 factorial x squared plus 1 over 4 factorial x to the fourth is approximately cosine x close to 0. Now, what is the minimum order of Taylor polynomial required to approximate cosine 2 with an absolute error no greater than 10 to the negative 1 or 1/10? We know that our absolute value of our remainder is less than or equal to m times the absolute value of x minus a to the n plus 1 all over n plus 1 factorial. Now, note, for this problem, we're not asked to use the polynomial above. We're asked what is the minimum order Taylor polynomial, meaning we want to find n. So we are trying to fill in as many pieces of this piece as possible and solve for when is that less than or equal to 1/10. So in particular, we know A is 0. We know A is 0. X is going to be 2 because we care about only up to 2 away from the center. Our center is at 0. We only care about cosine of 2. So that means we don't care about cosine of 3. And how well of an approximation that would be. We only care up to 2. So X is going to be 2. And M is the largest absolute value of the n plus 1 derivative on 0 to 2. While looking at our table, again, we don't know which derivative of cosine we're looking at, but we are looking at a derivative of cosine. So the n plus 1 derivative of cosine is either plus or minus sine. If we're looking at, say, the first derivative of cosine, it's negative sine. If we're looking at the third derivative of cosine, it's sine. Or the n plus 1 derivative is plus or minus cosine, because the derivatives of cosine cycle through these plus or minus sines and cosines. So we want to see, is there a value that sine and cosine are never bigger than on 0 to 2? And yes. For cosine, the graph of cosine from 0 to 2 looks like this. From 0 to 2. And the graph of sine from 0 to 2 looks like this. Does not get all the way back down. And this point here and the top of that curve for sine are both pi over 2. This is pi over 2. So we actually know for sine and cosine that between 0 and 2, the absolute value is going to max out. It's going to be the biggest at either 0 or pi over 2, and those values are 1. Cosine starts at the highest value it ever can be, and sine at pi over 2 reaches the highest value it can ever be. And since we are worried about the absolute value, sine is never smaller than -1, and it is never smaller, and cosine is never smaller than -1. Sine and cosine are both less than or equal to 1 on the interval 0 to 2. This means m is 1, because m is that largest value that n plus 1 derivative could possibly be. Meaning we have that our remainder of x is less than or equal to 1, m is 1, times x is the farthest we get from the center, that is 2, minus 0 to the n plus 1, over n plus 1 factorial. We want this to be less than or equal to 1 over 10. Meaning we are solving for when is 2 to the n plus 1 over n plus 1 factorial less than or equal to 1/10. The easiest way to solve things with factorials is to plug in values. So we're going to just plug in some values and see when does this become less than or equal to 1/10. So when n equals 1, we'll have 2 squared over 2 factorial. This is actually 2. That is bigger than 1/10. So it's not n equals 1. N equals 2, we will get 10 cubed over 3 factorial, which works out to be 8 over 6. This is bigger than 1, which is bigger than or equal to 1/10. So it's not n equals 2 either. N equals 3, we'll have 2 to the 4th over 4 factorial, which is 16 over 24. This is bigger than a half, which is bigger than or equal to 1/10. So it's not n equals 3. N equals 4, we have 2 to the 5th over 5 factorial, which is 32 over 120. And 32 over 120 is bigger than 1/4. And being bigger than 1/4, we also have that it's bigger than 1/10. So not n equals 4. N equals 5 will be 2 to the 6th over 6 factorial, which is 64 over 720. Don't know what that is exactly, but I know 70 over 700 would be 1/10. 72 over 720 would be 1/10. 64 over 720 is smaller than 1/10. Because it is smaller than 72 over 720. So that is smaller than 1/10. So n equals 5 works. So need at least 5 terms of the Taylor polynomial. Taylor polynomial to approximate cosine of 2 with an error less than or equal to 1/10. So we have the question answered. However, because we're dealing with sine and cosine, do want to go and look at something else. And that is, if I found the 5th term polynomial, p sub 5 of x, that would be p sub 4 of x plus that 5th term. That is the 5th derivative of x over 5 factorial x minus 0 to the 5th. Well, the 5th derivative of cosine is sine, and sine of 0 is 0. That means this term here is actually 0. And p sub 4 of x is equal to p sub 5 of x. So because that next derivative is 0, the 5th term polynomial gives us a small enough error. But in reality, because the 5th derivative at 0 is sine of 0, which is 0, p sub 4 of x equals p sub 5 of x. So we actually only need 4 terms. And if we were to actually calculate out the error, if we were actually to calculate out the actual error by using the polynomial and finding exactly what cosine of 2 was, we would see that we do achieve that small enough remainder at n equals 4. But for the remainder theorem to actually tell us the error is going to be smaller than 1/10, we need technically 5 terms. But that 5th term is 0, so it is not doing anything. So we actually only need 4 terms. Now, this little caveat is really only true because that next derivative was 0. So this is only going to happen, at least for this class, in cases of things like sine and cosine, where certain derivatives can be 0. But to answer our question, we need 5 terms.